Nitrogen is one of the most limiting nutrients in terrestrial and aquatic ecosystems, and that is despite the fact that we have an almost inexhaustible supply of nitrogen in the Earth's atmosphere. 79% of Earth's atmosphere is made up of nitrogen, but that nitrogen is not bioavailable. And that is because the dinitrogen has a really strong triple bond that makes it really stable, prevents it from reacting with anything else, and prevents it from being bioavailable. In order to make it bioavailable, that bond has to be broken and the nitrogen has to be converted into different forms, and some of these forms are bioavailable. So to break the bonds, we need a lot of energy. Lightning provides one of the ways that we can provide enough energy that then breaks that bond apart, lets the nitrogen react with oxygen, form various NOx's, reacts further with maybe some rain, and then that can be deposited, and this atmospheric deposition of nitrogen is one of the sources for nitrogen in terrestrial ecosystems. It's a relatively minor source, maybe 5, 6, 7, 8% of, on a global scale, the nitrogen demand of ecosystems is supplied in that way. So we as humans have figured out how to do this on an industrial scale as well. So where we can, under great pressure and with the use of a catalyst, take atmospheric nitrogen and hydrogen, which usually comes from natural gas or petroleum, and combine this to form ammonia, which is NH3, and that ammonia can be used directly as a fertilizer, but in most cases it's actually further processed to urea and ammonium nitrate. Before that pathway existed, which allowed us to apply a lot of fertilizer to our agricultural systems, it was plants, or it still is plants, that conduct most of this nitrogen fixation, making atmospheric nitrogen available to terrestrial and aquatic ecosystems. So this fixation is carried out by bacteria, and there's actually a whole variety of bacteria that do this. Some are aerobic bacteria, some are anaerobic bacteria, but the one thing they have in common is that they all have or produce an enzyme called nitrogenase, which allows them to do this kind of fixation. And some of these bacteria that do this tend to form symbiotic relationships with legumes, where the legume provides the bacterium with the food and with some nutrients, and in response or in return the bacterium conducts the nitrogen fixation and makes nitrogen available to the plant. So this nitrogen fixation allows the bacterium to form ammonia, which is in gaseous form, which also means that, well, this gaseous form is susceptible to volatilization or gassing off from the soil as well and returning back into the atmosphere. For this ammonia not to volatilize, if it is exposed to water, it may dissolve in water to form ammonium, which is an ion in solution. The ion, of course, can attach itself to cation exchange sites, but it can also be taken up by the plant as an ion in solution. So as we go from the gaseous form to the ionic form, we take up a proton, therefore we raise the pH of the soil solution. But if the plant takes up the ammonium, it would release a proton in order to maintain charge balance, and thereby this would actually be a zero-sum game in terms of pH changes in the soil. So while the ammonia and ammonium is available to the plant, it actually is another process called nitrification, which converts ammonium to nitrate, which makes nitrogen available to plants. In this nitrification process, we have bacteria that oxidize ammonium to nitrites, and then we have another set of bacteria which then oxidize the nitrites to nitrates. And these two groups of mostly autotrophic bacteria are called nitrifying bacteria. Surprise, surprise. So through these activities, they of course gain the energy that they need, and they make nitrogen in the form of nitrate available to plants. So this nitrification process is relatively quick, but it does produce nitrite as one of the intermediate steps. And nitrite itself is actually toxic to plants, but it's not there for very long because this conversion happens relatively rapidly. Well, and as the end product, we get nitrate, which is another ion, now a negatively charged ion, which means there isn't really much in terms of ion exchange capacity in the soil to hold on to this. We said in the past there is maybe some anion exchange capacity in the soil, but it's usually far less than cation exchange capacity. So a negatively charged ion is really susceptible to leaching. So the other thing that happens as part of the nitrification process, as you see, is that we release a whole bunch of protons. So nitrification tends to acidify soils. So the nitrite now, of course, can be taken up by plants. So we are immobilizing nitrogen that way. And the nitrogen is preferentially taken up by plants. So it's a much faster or a much more available form of nitrogen compared to ammonium, which would come through the decay of organic matter. So speaking of which, now the nitrogen that is incorporated into biomass undergoes the organic matter decomposition and frees up ammonium, and ammonia in the process makes that bioavailable again. And then, like we said earlier, the ammonium as a positively charged ion can be stored in soil, for example, on cation exchange sites as they exist with clay and organic matter. So in soils, it usually is that we have the vast majority of the available nitrogen locked away in the organic matter in one way or the other. So this form of nitrogen is the most important form that cycles around in the system. So lastly, the nitrate can also be undergoing a process called denitrification. And it's actually a multiple step process where we go from nitrate eventually into gaseous forms of nitrogen or dinitrogen in the very end, which can then be re-released into the atmosphere. And that is happening under anaerobic conditions. So it's an anaerobic reduction. Anaerobic bacteria gain their energy from this process, and the soil system will lose its nitrogen that way. So the other nutrient we said we're going to spend some time on was phosphorus. And phosphorus behaves in the environment very different than nitrogen. With nitrogen, we had this large reservoir, if you like, in the atmosphere. It wasn't bioavailable, but through fixation, we could make it bioavailable. And then the ionic forms of nitrogen remain relatively stable in soils. They cycle through soils, might eventually be lost back to the atmosphere with denitrification, but once we have it bioavailable, then it changes forms and stays bioavailable. Phosphorus is different in that it's relatively rare to start off with. There's only about 0.1% of the Earth's crust that contains phosphorus. And then phosphorus also is very reactive. So we don't actually find any elemental phosphorus in the environment, but phosphorus will violently react with oxygen to form phosphoric acid, and then even that will continue to react in the environment. So here you see that phosphorus exists as an anion, and that's pretty typical. It will usually exist as an anion in the environment. So if we put this phosphoric acid in the soil system, we can look at how bioavailable some of this is. So we have the 0.1% concentration of phosphorus in the crust here indicated on the y-axis, and the pH on the x-axis, because the availability and the forms that phosphorus exists in nature is very much pH dependent. So the green line here indicates the sort of bioavailability of forms of phosphorus. So it's mostly dihydrogen phosphate ion or hydrogen phosphate ions. And you see that it sort of peaks between 6 and 7 pH. And the other forms are also available, but less available. So you see that compared to the 0.1% concentration in the crust, the bioavailable forms of phosphorus are relatively small. So where's the rest of it? If we look at the higher pH values, if we go to more alkaline conditions, we find that it reacts readily with particularly calcium, and it forms, amongst other minerals, a mineral called apatite, which is the mineral that we most often mine and then introduce to soils as an amendment to increase the phosphate, the phosphorus concentration. As we go towards more acidic conditions, we also find that phosphorus tends to form coatings around sand and silt particles. It also likes to attach itself to cation exchange sites that replace in the OH groups. And if we go to more acidic conditions, then it reacts readily with aluminum and iron to form hydrous oxides of these. And then if we go to really acidic conditions, then there's also some chemical fixation with soluble aluminum, iron, and manganese. So overall, most phosphorus that is in soils goes into forms that are not mobile and that are not bioavailable. So in that sense, then phosphorus is likely to be retained in a solid form. It's unlikely to be lost due to leaching, which is very much different than what we had for nitrogen. So the actual phosphorus cycle is now relatively simple and straightforward compared to the nitrogen cycle, and it is mostly because phosphorus is not very available, it's there in low concentrations, and it has a really strong dependence on pH. So let's say we have a pH of 6 to 7, and we have some dihydrogen phosphate available in solution, which can be taken up by roots. And what we've said previously about phosphorus root uptake and how it enters the root, here diffusion plays a much bigger role than mass flow because the concentration is so low in the pore water. And we also have the microbial facilitated access of phosphorus to plant roots, contributing to root uptake. The phosphate that is locked in the biomass eventually finds its way back into the soil, either as living organic biomass or stabilized organic matter. And then it can, of course, mineralize and immobilize just like any other nutrient that is in organic form. The other inorganic forms are mineral phosphorus and absorbed, various ways of absorbed phosphate. The mineral phosphorus, of course, provides one of the sources of phosphate to soils. So we have weathering of primary minerals, bringing a supply of phosphate to the soil. This is going to be most important, of course, for young soils versus for older soils like oxasols. Most of the phosphate contained in the original primary minerals will have weathered away already and will be less available. Now, these soluble phosphates can, of course, precipitate out, so they can form things like apatite again, and thereby make it plant unavailable. And the same thing with sorption and desorption, where we mostly find unavailable inorganic forms of phosphate in soils. That also has the consequence that because there is so little of it in solution at any given time, that the potential for it leaching or being lost due to leaching is quite minimal. So for phosphates, then the ways that it moves offsite are going to be related to harvesting. So any phosphate that is in the biomass and gets moved offsite will be lost to the system, and phosphate that is in absorbed phases or as part of the organic matter on the soil surface can be moved away by wind and primarily water erosion, and then lead to unwanted growth in other ecosystems that were previously limited by their phosphate availability. So to summarize what we've learned about nitrogen and phosphorus, behaviors in the environment, how it cycles through the environment, let's contrast the two here. For nitrogen, we've learned that especially in the form of nitrate, it is very mobile in soil water and has a really high potential to being lost due to leaching. So even with really good management, it's oftentimes very difficult to keep nitrate in a particular system. Phosphorus, on the other hand, is not very soluble. It's there in low concentration, so the potential to moving it offsite or losing it due to leaching is quite minimal with phosphorus. With nitrogen, we learned there's another loss mechanism, and that is to either volatilize ammonia or denitrify various forms of nitrogen in the soil. That happens usually under anaerobic conditions, where it's then returned to the atmosphere again, either as dinitrogen or various forms of nitrous oxides. For phosphorus, there's no volatilization losses, but for both of them there are runoff and erosion losses. And I made these arrows about the same size, or they are identical in fact, because the potential for runoff erosion as a loss mechanism is about equal for nitrogen and phosphorus. But you'll see that because there is very little other loss mechanisms for phosphorus, proportionally it is much more important for phosphorus than it is for nitrogen. The other loss mechanism that isn't depicted here is the one with crop uptake and eventual harvest. In both of these cases, then the harvest and moving offsite of biomass, of course, is a loss mechanism for both of these. So for nitrogen, we have about 95% of the soil nitrogen that we find in organic form. It's locked up in the organic matter in various ways, in the more labile or more stable organic matter, and then a small proportion of the available nitrogen in soils is in inorganic form. With phosphorus, it is the complete opposite. There is a small percentage of it in organic form, and most of it is locked away in inorganic forms, where it has either absorbed or it has precipitated out in mineral form. The available forms of nitrogen are either ammonia or nitrate, and then there's of course also some small dissolved organic nitrogen, which is of importance, but ammonia and nitrate are the most important ones that are bioavailable. For phosphorus, it's dihydrogen phosphate and maybe hydrogen phosphate as well. No other forms are really available to living things. For nitrogen, and the nitrate, we've said already, is very mobile, very dynamic in the system, and in contrast, dihydrogen phosphate is much less mobile. And overall, phosphate, especially since most of it turns into inorganic form, precipitates out or absorbs on surfaces, is not mobile at all versus nitrate and nitrogen, which is much more mobile in the system. As a result of that, if we do add additional nitrogen to a field in forms of fertilizer, most likely that added nitrogen will leave the system over time. So continuous applications of nitrogen are needed if there is a deficiency in it to upkeep crop production. There's very little mechanisms available to keep it in the system for long. For phosphorus, most of the added phosphorus will actually accumulate in the system. Of course, it won't accumulate in a form that is bioavailable, but you're accumulating inorganic phosphates, which then through weathering or desorption become bioavailable. So continuous additions of phosphorus will lead to a buildup, and then eventually there's enough phosphate in the system to support plant growth.